We're now happy to listen to Tone Ho. We'll speak about verifying cryptographic code with Aeneas.
It was used in many places, including the Python standard library. If you look at the bug, it's a bit subtle. So in order to trigger it, you need to call some very specific function with a buffer that has a very specific length. And then you need to call it again with a function with a buffer that has some other very specific length. So it's all about corner cases. Now, a natural question is this really important? It looks like it's very, unlikely to trigger. But the problem is, it's not about, random bugs. It's about the fact that there are attackers out there who will look at your code and will look for vulnerabilities. And if they find one, they will systematically use it. Okay, so that's the keyword. If there is a vulnerability and it can be exploited, it will be systematic. Once again, albeit that was one buffer overflow. And from there, it was possible to mount massive attacks. So this is why we want to have very high level of guarantees. This is why we want to have verification. And in the context of this talk, I'm going to focus on functional correctness. Now, let me give you a very concrete example of the kind of things we do. So we often need to compute a modulo in cryptographic code. And the question is, how do you do that where X is a secret? So the problem is, so it might be derived from a secret key, for example. The problem is that the modulo, the remainder operation, is non-constant time. So the time it takes to execute depends on the value you put, right? Mm-hmm. So an attacker can measure that and deduce information about this value. And this is a very classic, common way, a very standard way of breaking private keys. So there are many ways of solving this problem. I'm going to look at a very, very specific example that comes from SymCrypt. So let's say you want to compute A plus B modulo the prime number 3329, where A and B are themselves smaller than 3329. So you're doing operations modulo some prime number, right? We want to do that. As I mentioned, we can't compute the modulo here. Now, something we can use is that all we need to do is compute the sum. And if we're not in bounds because of properties of the modulo, all we need to do is subtract 3329, and we need to do it once. Now, we can't use this if then else here, because if then else is like the modulo is non-constant time. So we need to find a different way. We need to implement a conditional subtraction in a constant time way. So here's a way. The way it works is you eagerly subtract, and then you conditionally add 3329 back to cancel the subtraction if you did not need to do it in the first place. The way it works is if you did not need to do it, you get an underflow. So this value here has a lot of ones on the left. In particular, it has at least 16 ones. Then you can shift it by 16 and you get a mask. And you can use it to mask 3329 again. So 3329 holds on 12 bits, so that works. And then you add it back. In the case you actually needed to do the subtraction, there is no underflow here. This value is small, so the mask is equal to 0, and you do not add anything back. Okay? So, okay, I'm sure many people do not get that example. The point is, we have a very simple thing to implement here, right? We just want to compute a modulo. But we have to do all sorts of shenanigans to make it work because of various constraints, right? Now, this example is very simple, actually. So the simplest, most simple I could find in SymCrypt. There are many, many other examples like that. And very quickly, when you have a complete cryptographic library, you have implementations that are architecture specific, you have many algorithms, it becomes very quickly hard to make sure that everything works out. Okay, so we want to do verification. We're targeting Rust code for several reasons. And we want to do verification with Lean. Why Lean? There are essentially two reasons. One, it's highly extensible. It's designed to be extensible, and we want to leverage that. This is very important, for example, to implement custom automation, and we need that. Another important reason is the community around it. So, for example, in the context of doing cryptographic proofs, it's very useful to have a complete mathematical library just at our hands. It's a lot of maths, cryptographic code. Also, it's very useful to be able to rely on a foundation that maintains the tool. So Lean is not completely a research project anymore. It has really turned into a product. And there is a lot of value into being able to, when you have a problem, to go see a foundation with more than 20 engineers, essentially, and say, we have this and that problem, and we know we're going to be listened, and we know this foundation has the manpower to fix the issues. There's really a lot of value into having that. Now, we want to link the two. We want to link Rust and Lean, and this is where the Aeneas toolchain is. So that's essentially a bridge between the two, and it works as a compiler from Rust to a Lean model. Once you're on Lean, you can then state and prove the theorems you want, in particular functional correctness theorems. And we decided to have this design also because it gives a very clean modularity between software engineers and proof engineers. So there are many choices you can do there. Many toolchains choose to have the two in the same place. We decided to have a separation of concerns, in particular because we need different expertise here. So the software engineers, it's very hard to train them to become proof engineers, but the reverse is also true. You can't take a proof engineer and turn him into an expert in writing cryptographic code. There's a lot of expertise in there. So I cannot write cryptographic code, for example. A very important thing is that on the left, we have low-level imperative code that uses pointers, but we can leverage the type system of Rust, in particular its system of ownership and borrows, to generate a model that is pure and functional. So we abstract away pointers, we abstract away reasoning about memory, and that is essential into scaling the proofs. So this is one of the key ingredients to make that work. I'm going to give you a quick explanation about that. One of the difficult things to reason about is these sort of functions where you dynamically play with pointers. For example, here, this choose function takes as inputs two mutable borrows. So that is to say two pointers with exclusive read-write access, and dynamically returns one of the two. Okay, so this is the typical kind of patterns that is hard to reason about. And here we can see it in this example. So you get access to actually a pointer that points to X. You can use it to do an in-place update, and then later you can get access back to X and Y. Now in Rust, there is this notion of lifetimes here that links the input borrows to the output borrow. What it tells us is that for as long as the output borrow is alive, we have to consider that the input borrows are alive, and so we can't access the values they point to. Okay. Now here the lifetime alpha goes from the call to choose and ends just before the assertion. So from here to there we can use Z, and afterwards we get access back to X and Y. You can't use Z anymore. The key idea we use here is that this essentially defines a scope. So there is a scope during which we can use that, and when the scope ends, we get access back to X and Y. So that's what leads to this translation. So at call site, we retrieve the value of Z, which is a purified version of Z. We can use it, and then later when the lifetime alpha ends, we use a continuation to propagate the last value we put in Z back into X and Y. Okay, and this choose function that returns this continuation to make the lifetime apparent, it returns either X or Y plus a continuation that consumes Z and returns either an updated value for X or an updated value for Y. So that's the whole idea behind the translation. It's a modular translation, so it's type-driven, and it relies on this notion of backward functions. We call these continuations backward functions. How does it work? Importantly, in order to make it work, we need to track at every point in the program who borrowed what from who. So that's the way we can infer when we need to insert backward function, what it consumes, what it gives back. And we do so by doing some sort of a symbolic execution that keeps track of an environment where we abstract away the heap and where we treat borrows and loans as first-class values. So for example, initially we just have a mapping from X to the value 0. And when we create a mutable borrow, we replace the borrowed value with what is called the mutable loan. The borrow itself is a mutable borrow value, here are the value 0, and we link the two with a fresh loan identifier. So here we just say P mutably borrows the value 0 from X, or the reverse, X is mutably borrowed by P. And importantly, when we need to access back to the borrowed value, well, we end the loan, and we do that in a lazy manner. We end borrows as late as possible. So this gives a lazy semantics of borrows and loans. For function calls, we leverage the signature of the function, in particular the left-hand constraints. And we introduce a device that is called region abstraction. So it's a way of attracting part of the borrow graph by linking input borrows and output borrows. Interestingly, this implements a borrow checker. And this is actually a fact that we have formalized. So we proved that there is a forward simulation between this and a semantics of Rust where we explicitly model pointers and their reference and these sort of things. So this is a pen and paper proof. There is a mechanization ongoing, and there is also an ongoing work on formalizing the translation. Okay, so that's for the high-level idea. Now let's do a small demo.
You're not sharing the lean.
Okay. Let's do that.
Yeah, that's good.
Okay.
Yeah.
So,
but not in the room. It's great online, but in the room.
Okay. Can we?
Probably need to close the sharing and reopen it.
Very good. Okay. So on the left, I'm going to show manually handwritten code, Rust code. On the right, we have the result of the translation. So this is choose. There is one difference with what I've shown on the slides is the fact that we need to make it explicit that the function can fail. So we have this result monad.
Is it possible for it to be slightly bigger?
Okay, I can't do more than that. Okay, but this prototype is the same. Here we have a very simple mul to add one function. I'm going to use it to show you how the proofs work. As you can see, we need to disregard what's going on. We need to introduce intermediate-led bindings for the various operations. Increment is interesting because there is a lifetime alpha, but this function is a bit degenerate in that it does not return any borrows. So the way it works is it has output type unit. So in theory, we should return a unit, a pair of a unit, and a backward function. The problem is the backward function does not. Sorry, that's the one here. So we should return a unit and a backward function, but the backward function does not consume anything. It just gives you an updated value. So it's just a value of type U32. And because there is no point in returning a pair of a unit in something else, we simplify that to we directly return a U32. So for this kind of function that just receive a mutable borrows input, it leads to a, I think, quite natural state passing style function. And you can see how it works here, where we call using curve several times, we just thread the call to X through the various functions. We have reconstructions on loops. I'm not going to show you that. The important thing is we translate loops to recursive functions. And importantly, we can support traits. And the reason comes from the fact that we have a directory translation, so it's modular. So traits are essentially type classes for Rust. For example, here we define a trait counter that says that you implement counter if you provide a method increment that takes a mutable borrow to yourself and returns a usize. You can very naturally implement counter for usize itself, okay, like this. And in the translation, we model traits but with structures. So we say that we implement counter if you can provide a structured counter, like here, where we make the type of the counter explicit. So it's implicit in Rust, we have to make it explicit. And where you provide a function that consumes an element of type self and returns a usize plus an updated value of self. Okay. And then implementing the model for counter is very straightforward, and you can use it also in a function that is polymorphic. So for example, here we say that we receive a counter of type T, where T must implement counter, and in the model, we need to make it explicit that you receive an instance of counter. And finally, we get to the mod add function. That is very similar because there are no borrows. So how do the proofs work? Well, we implemented a proof mode to leverage Lean to solve things. So, for example, for mul2add1, so mul2add1 once again is this function where you compute x plus 1. We're going to prove that if 2 times x plus 1 is in bounds, so it doesn't overflow, then mul2add1 of x successfully evaluates to some value y, so it's total correctness, and y is equal to 2 times x plus 1. Okay, so very simple. Importantly, we use x.val and y.val. That means x and y seen as unbounded mathematical integrals, right? Because they're machine integers. The first thing to do is to unfold the function mul2add1 to see its body. And then we have a tactic step that essentially looks at the goal and says, oh, we first need to reason about this addition. So it looks up the proper theorem, it instantiates it, and then it proves on the fly that you do not have any overflow. So then we get to goal where we have I that is linked to 2 times x plus 1. The upper row x means x.val, because it's just some syntactic sugar. And then we can proceed forwards, and then we can finally close the goal. And once we've proven a theorem like that, we can annotate it with the proper attribute so that we can use it later. So for example, in mul2, in this use mul2add1 function, we use mul2add1. We can either directly provide the theorem to step for it to use it, or we can simply let step look up the theorem because we registered it in the database. But these are, of course, toy functions. Mod add is a real function, comes from SymCrypt. Very quickly, it becomes very tedious to write all these calls to step. So we have this step star variant that goes as far as possible. So for example, here it goes through the whole function and just leaves the final goal, which requires bit blasting. We do many things to tweak the tactics and make the user experience as nice as possible. So for example, if you want to see the various proof steps, you can write add a question mark here, and it will automatically generate a proof script so that you can go through all the steps and understand what's going on. So it's a very common way of working. You expand, you look through the steps, you solve the problems, and then you fall back. And finally, the final proof obligation is discharged by using this the BVD tactic, which another who uses a BVD side, which is a bit blaster. So going back to the presentation. Okay, so our main use case today is SymCrypt. So SymCrypt is Microsoft's open source cryptographic library. Importantly, it's the go-to library for cryptography to use in Microsoft. So whenever someone needs to use cryptographic code, the default is to use SymCrypt. In particular, it's being used in the Windows kernel and in Azure Linux. You guessed it, it's critical low-level code that runs on billions of machines. The good news is it was originally written in C, but we're now moving towards Rust, and we verify the Rust code at the same time by using Aeneas. There are quite a few constraints. First of all, we need to verify the code exactly as written by the project team. We do not modify the code. We cannot modify the code. I will come back to that. And at this stage, we have around 4,000 lines of verified code, and it's ongoing. Very importantly, we're at the end of an experimentation phase during which there were two goals to solve. One, we needed to show that it's possible to move towards cryptographic code written in Rust. It's actually a really tough sell because, for example, you don't get anything in terms of performance by moving from C to Rust, but this got validated. And the second point was, of course, to prove that we can scale the proofs while doing so. There are several ingredients that are making this verification effort possible. First, the Rust type system, the fact that we have this pure model, Lean's extensibility, and lately, the use of large language models. Now, there are many nuances to say about large language models. I will come back to that. We made the choice of having a clean separation between code and proof and between various expertise. It does not mean that the software engineers and the proof engineers live in two different worlds. Okay, we need to communicate, interact very closely. One way of doing that is to have dashboards. So we have dashboards, like at the dive, that we use to report the state of the verification, what is verified, what is not. And also we use them to show them the specifications. And we make it so that they can, click on definitions so that they can see, oh, okay, here there is a precondition that refers to a well-formed array predicate. What does that mean? And they can see that whether it's open in Lean. It's very important for them to see these sort of things. Importantly, I will not make the software engineers write Lean code. I will not make them write Lean proofs, but this kind of works. They can read the specifications, and they like these dashboards very much. Now, we're not talking about any kinds of engineers. Cryptographic engineers, they have to implement code following RFCs. The RFCs are math heavy, so they're used to reading these sort of things. If you ask me, can any engineer read these sort of specifications? I don't know, probably not. Okay, I mentioned that we verify the code written as is, and this is very important. So a very common practice is to adapt the code so that, the verification is amenable. So you remove problematic patterns, you remove problematic features. In the case of SymCrypt, we can't really do that because the code is very constrained. So we have, at the beginning, a very large design space, but there are a lot of constraints that cut into the design space. For example, the code needs, of course, to be performant. It needs to be constant time. There are many constraints linked to design choices, many more constraints linked to the fact that it needs to run in the Windows kernel, and many small things like, for example, it needs to run into very constrained environments that are constrained memory-wise in such a way that even the size of the binary is a problem. And if you want to know, in that context, LLVM is a problem because it generates very big binaries and the engineers have to fight with that. Now, the problem is that very quickly of course, we wanted to adapt the code to make the verification simpler, but there is not much jiggling room left to do so. A simple example is at some point we wanted to modify a primitive called ASGCM to use traits. The problem is that for those who know, if you use traits in Rust code, it leads to monomorphization and specialization at compile time. That is, it blows up the size of the binary, so we cannot do that. Now, if we're really precise, it's not as black and white. We can actually modify the code a bit, but we had many discussions with the SymCrypt team, and we asked them at the beginning of the project, okay, can we change this? Can we adapt that? And it always boils down to the same problem, which is, does it have a big impact on the code? Now, if it has a big impact, you can't make the modification. They're not happy with it. If it has a small impact, well, you can do it, but does it really help? That's the problem. So in particular, what you save by doing these small modifications is completely dominated by what you do not get by not being able to do more invasive modifications. So we quickly came to the conclusion that if we want to really verify this production code, then we can't modify it. We have to verify it as it is. We actually still modify it a bit, or we actually rather push for modifications. In the end, it's always the SymCrypt team that decides what gets modified, but it's only to make it better. So for example, it regularly happens that when you do the verification, you notice optimization opportunities. For example, there is in cryptographic code, say you have something like a reduction that doesn't need to happen. You can just remove it to save cycles by doing that. So we can say that to the engineers. But in the end, the modifications we push for are they really follow software engineering criteria. We can push for modifications if it improves the code from a software engineering point of view. We do not do that from a proof engineering point of view, so that the proofs go through. We also try to limit annotation, so we have to annotate the code a bit. For example, to explain that we are not going to verify the FFI, we're going to ignore it, or to opacify, that is, axiomatize some functions we can't model because it uses unsafe code. But we also try to keep that, as limited as possible and as non-invasive as possible. And of course, we need to communicate with the engineers, but we do so by using the dashboards. Okay. Now, once you verify the code written as is and you do not adapt it for the verification, you bump you immediately bump into many problems. So the toolchain immediately hits walls. One problem is, of course, the functions are huge. So this one, for example, takes 3 times the screen. There are quite many functions like that. And in this context, your tactics, your solvers must work in huge contexts with hundreds of hypotheses. And so we had to work a lot on the tactics so that it would work. And this is why it's very useful to be able to really tweak the toolchain, bend it into the direction you want. It's not just about writing automation, it's also about many, many small things. So for example, when you use the apply or the conquer tactic, it's useful to be able to tweak the reducibility settings so that it does not trigger a very expensive reduction to weak head normal form that takes minutes. So, it's a lot about very small details, but that you need to be able to tweak. And we have many other things. So we have our own to elaboration because the Lean's default to elaborator does things that we don't want to do. And that matters a lot when doing the proofs and many other things like that. Another thing we had to work a lot on is also the subset. So intuitively, cryptographic code does not need much. It's all about arrays, right? But that's true in C. That's not true in Rust. If you want to write idiomatic Rust code, you immediately use iterators. So the engineers use iterators. We need to give them iterators, in particular mutable iterators. It means you need to verify higher order code. You need to support nested mutable rows, all these sort of things. And there are many other small features like that you do not necessarily notice just by looking at the code. So for example, a very common pattern in Rust is this trying to unwrap. So when you convert something like a slice into an array. Now, the unwrap function requires some type to implement debug. The debug instance is typically automatically generated through derived clauses. And if you do that, it uses dynamic traits. So for those who don't know, dynamic traits are basically classes, like in object-oriented programming. So it uses the table. It's not hard to model in Lean. You just have an existential file. The problem is that you need to support a lot of features like that. And you need to support it in the translation, you need to support it in Lean, and it very quickly stacks up, even for code that is seemingly quite simple in terms of the kind of things you do in terms of subset, right? I mentioned these derived clauses. An interesting consequence of the choice of having the separation between the code and the proofs, so jointing the model and then setting and proving theorems about the model, is that we see the code post-elaboration. So in particular, there is no difference in the model we generate between handwritten functions and automatically generated functions. It can be very useful to reason about them, especially when you need to reason about clone instances or partial rates instances. These sort of things happens a lot. And having the model at hand that you can look at is quite convenient. So there is no separation between the two. Okay, so what's the state of the verification? So for the beginning, we focused on post-quantum cryptography. The natural question is, what is the point of deploying post-quantum cryptography today when the biggest quantum computers have maybe 100 of logical qubits? So we're nowhere near breaking classical cryptography. And the reason is that even though we may need to wait many years before being able to break classical cryptography, we're already vulnerable to a class of attacks called harvest now, decrypt later. So if you're powerful enough, you can just observe the network, save all messages, and then a few years later, when you actually have a usable quantum computer, you can break these messages. Not everybody can do that, but some can do it, and for some messages, it's worth doing it. A good thing with cryptographic code is that there is a clear specification. There's an official specification given by the RFC. So this is the kind of things we get. So this is for what is called the number theoretic transform. It's one of the important algorithms of the first primitive we worked on, which is called MLChem. As you can see, it's very algorithmic. So it's really meant to describe a reference implementation. Okay. Now, if we look at just these two lines, they implement a multiplication of a power of some constant zeta modulo the prime number 3339. So the mod example I showed comes from this code. The implementation looks like this. Yeah. So there's quite a big gap, and this is only the portable version. Hence, once again, the need for verification. A good thing with Lean is that there's a nice modeling notation that we use to write the specifications. And we really put a lot of efforts into making the specs look as close as possible syntactically to the RFC. And this is very important because the spec is the source of truth. If there is any mistake in there, the final theorem does not really have any value, right? So there is this syntactic closeness. The fact that this, the RFC is an algorithm gives us also an executable specification. This is very useful to test it. So we test the specs against test vectors. And finally, something that is not necessarily obvious is that we statically check many things, in particular bounds. Okay. So once again, the goal is to have extremely trustworthy specifications because, well, this is the source of truth. Now, given this spec and the model Aeneas generates, we can set and prove functional coordinates theorems. So do not look at the theorem. What's important is that we prove essentially that the model of the code can be swapped with the specification modulo some conversions. Okay, so we say that the entity in the code called on some input array, once converted to a polynomial, so the RFC here uses polynomials, is equal to the specification called on the input array seen as a polynomial. Okay. So as of today, as I mentioned, we have around 4,000 lines of verified code. And very lately, we started using AI agents very seriously. So the latest result we have is we were able to fully verify a cryptographic primitive called ASGCM within a week with one AI agent running sequentially. So no parallelism, no sub-agent, just one agent. This is not the biggest primitive, this is not the most complex, but once again, this is a sizable primitive, and this is low-level production code written by engineers with no background in formal verification, and they write the code not to verify it. Okay, we do not modify the code. So essentially, by combining proper ingredients like extensibility, the pure model, and an AI agent, we can go super fast. And we're reaching, like today, with this primitive, we're able to verify more than 100 lines of code per day. Once again, this is not any code, even though this is not the most complex primitive. This means that in the context of this project, the proofs are not the bottleneck anymore. This is in the context of this project, okay? This is a very specific project. This is cryptographic primitives for which we have a very clear specification, for which we prove one property, which is functional correctness, for which we push the toolchain because, this is our main use case. I'm not saying you can do this for anything, but it's very useful to know that we can do that already. So, as I mentioned, this works because we have the pure model, we have automation. This is a very specific class of programs. And there are many things happening behind the stage. So expertise is really crucial. We regularly need to dive into the proofs to understand what's going on, what the AI is doing wrong, and also review the theorems, the AI proofs, supervise it. So expertise is really, really crucial into making it work, even for a very specific class of programs. And a typical problem is that agents have very limited context. So something that happens a lot is the agent tries to do something. In order to do it, it needs to learn some context. By doing that, it forgets something else. So it needs to go back to that. By relearning this context, forget what it learned here, and it enters into a loop. And you need to intervene, do something, improve the tactics, whatever, so that it eventually exits the loop. So these sort of things happens a lot. But the thing is, even though there are still many things we need to do for it to work, it had a deep impact on the way we work on our verification methodology. So until now, we would put most of our work into the toolchain to make it really scale. And we try to have around 3/4 of our time investing into the toolchain and the remaining into the proofs. And so the idea was to say, hey, we push a bit on the proofs, and whenever we identify a problem, a place where we need to grind too much, we go back to the toolchain, we improve it so that we can go back to the proofs, go fast, do big pushes, and make progress in the proofs without spending most of our time doing grind work, essentially. Now, very quickly, the time we spend in the proof is converging towards zero, and this comforts us into the fact that the value really is in the toolchain, at least for this project. I'm not talking about any kind of code again, once again. Okay, so that's SymCrypt, that's cryptographic code. What about going beyond cryptographic code, right? A big problem we have today, is that the functional model only works for a subset of us. So we need to go beyond. There are things that are non-functionalizable. So for example, async await, IO, things like intermutability, which is essentially unrestricted aliasing, but that relies on dynamic checks, concurrency. So there's a question we're exploring today, which is how can we go beyond the pure model while keeping the proof simple? And the idea is to have some sort of a hybrid model where we leverage the pure translation as much as possible, and when necessary, have a more complex stateful model. And a natural question is, of course, how do we reason about such a hybrid model? And a natural answer is, of course, separation logic. So I'm working with some people here on that, actually. The key idea here is that the pure translation is very compatible with separation logic. So this notion of backward function that I introduced to functionalize what it means to have a lifetime is essentially a way of functionalizing a magic wand. So if you look at the choose function again, in theory, it should be possible to prove the following 4 triple. So essentially, choose consumes 2 pointers and gives you a pointer whose value is given by the translation, plus a magic wand that you can apply when you end the lifetime. And it gives you back X and Y where the values are given by the backward function. So there is this very natural link, and we want to exploit that to connect what we do to this more expressive subset by using separation logic. Okay, that's it. Thanks for your attention.
Thank you, Sean-Ho. There are questions in the room? Well, okay, many questions in the room. Yes.
So you mentioned that constant time execution is very important. But of course, when you translate, you do not know. So is there a story for this in the
Yeah.
Can you repeat the question?
So the story is constant time is very important. Do we do something about it? So constant time is very tricky because, so first of all, constant time, as I mentioned it here, is a programming discipline. So we forbid operations like doing a modulo of a split data, doing a division, doing a branching. This prevents you from the worst, but it does not actually give you any guarantees about the code in the end. So there are 2 reasons. The first one is the compiler does not necessarily preserve anything, and compilers are very clever, and when they detect something like the mode add function I showed, and when they notice they can undo the masking, we call that masking, they will happily do it. So they do not preserve that. So if you want to have any guarantees, you need to look at the binary. And even worse, there are things like speculative execution, so typically Spectre. So we do not do anything at the level of the source code. We do not verify any constant time discipline. What we do is we analyze the binary. And we do that by using a tool called Revisor so the problem is there is no official leakage models for modern hardware. So the tool learns leakage model by executing operations and essentially trying to trigger Spectre attacks on small snippets of code. And then we do a symbolic execution on the binary to check if there is leakage. But that's basically the best we can do.
Yep.
The notion of this backwards function, the presented, I'm sorry, I don't remember the slide number, is somehow related to the concept of a lens.
Yes.
Is that accurate?
Yes, that's essentially a lens. Yeah, no, that's.
Is it the same thing, or are there any sort of like caveats?
I'm not an expert in category theory, but to me, it's the same. It looks like the same.
Thank you.
Other questions? Yep.
How would you change your translation and accommodate concurrency?
So the idea is to say, how would I change the translation to accommodate concurrency? So a simple thing is as follows. So you have a mutex, you lock it, you get the value inside that is guarded by the mutex, and then you unlock. The idea would be to model the mutex lock and unlock operations in a stateful way and use the translation in between for the critical section. That's one of the things we have in mind. Yep.
So you mentioned you obviously can't change the code. And I would assume because you're so careful with crafting the specs, you also probably don't change the specs to accommodate the code. Do you find yourselves proving kind of intermediary functions with functional equivalence until you get something that's amenable to the spec?
Yeah. So we do these sort of things, and this is definitely a problem. We're working on improving that. So yes, there is a huge gap between the spec and the code, which is made even bigger by the fact that we do not want to compromise on the spec. So for example, if the spec like uses nested for loops to explain how to initialize a matrix, we keep the for loops. We do not say, the matrix is, like there is a matrix.often function that allows to say, oh, at the cell of this is I and j, simply equal to that. We do not use that. So we need to introduce intermediate theorems for that. And as I mentioned, we're working on introducing ways of making it as simple as possible.
Did you find issues in the RFCs, given that you took this very cool approach to have the specs as close as possible to the RFCs?
The question is about the RFC or the code?
RFC.
Well, Cedric can, I think, found issues in. No, it was not an RFC.
Yeah, I can maybe mention a couple of things. So typically, the standards are super. They are not that many bugs in them. So for some of the new algorithms that are going standardized, we try to formalization using and it's actually quite easy to generate automatically some sanity checks, like whenever there is a sentence in the standard that says this is an inverse of that function, and you can actually prove it, and if it's not there, we can raise a flag so you can prove, like earlier to the found on compress and uncompress, you can prove that decryption is an inverse of encryption. If you cannot prove that, then you will flag doubtful. So concretely, we found a couple of bugs in this preliminary standard general specs. Like there was a typo, there was a 49 instead of 59 in a red dimension somewhere, and there was a condition that was stated in the analysis but not in the main body of the description. So we can find small discrepancies, but not regular. Nothing scandalous so far.
I have another question.
Yep.
So about the translation from C to Rust, how do you make sure that it's faithful?
We do not. Oh, yeah. So the question is, when going from C to Rust, how do we make sure that it's stateful? Faithful, sorry. We do not. I mean, we verify the Rust code in the end, but of course, I mean, if you want to make sure it is faithful, you will need to verify the C code as well. This is definitely not something we want to do. Yes, we can imagine that, but the idea is really to go towards Rust. So for now, the engineers have started by writing new implementation in C and then porting them to Rust so that they can compare.
I mean,
We're planning to move, yeah.
Will there be some form of Aeneas for C also?
Well, it's very hard because one of the key ingredients is we use borrows and ownership. C doesn't have that. And I don't see myself designing an annotation language for C to make it work in C.
Yes.
Have you found any bugs in the Rust implementations?
So we found minor issues. We found a bug in Flowdocken in particular, with the caveat that this bug would likely have been spotted had the implementation been tested more. I really want to insist on the fact that it's not about finding bugs. It's really about providing guarantees, right? And verification is the only way of having that. You want to be sure when you ship the code, you do not have any bugs. And so, you're safe. We did find optimization opportunities there.
Just one question.
So there are some libraries, right, in Rust, I mean, those libraries from SymCrypt which you have proved, I think that exist also in other Rust grades. So in principle, if you prove them for the Rust code from SymCrypt, you should be able to reuse them to prove other Rust grades. Rust script, I forgot which was the grade used by Leaf-Signal, for instance. So you get for free proofs for.
Okay, it's interesting to know. Yeah, I'm not sure which library you're referring to.
So Leaf-Signal.
Because of libcrux.
Yeah, but for the primitives, I mean, Aeneas and so on, I mean, then they're from Rust script, so put them for.
Importantly, yeah, I think it's important to insist on that. It's not enough to verify one cryptographic library, because cryptography is very specific. It has a lot of constraints. For example, the constraints of SymCrypt are not the same as the constraints of Signal or Google or whatever. So it's very important today for the SymCrypt engineers to have their own library. Because, for example, you can't just ship any code into the Windows kernel, typically. So that's the reason why there is, all these libraries, and so we need to duplicate this effort.
No, the other, it was direct.
Oh, okay. Yeah.
Then
Yeah. But maybe they have different constraints, so they can consume our code.
So there was one question online about the process you used to formalize RC to Lean.
So until recently, it was completely manual. So we just read the RFC, port it to Lean. Now we're playing with auto formalization. So the starting point, so it's a very slippery slope, because once again, the spec is the thing you need to trust. We're playing with that in the context that the criteria for us is really that the spec must exactly match the RFC. So if there is any doubt, you reject the spec. So it must be, in particular, very easy to audit. In this context, there is a real question, which is it okay to have the spec partly generated by an adversarial agent? What we see so far is there are a lot of issues. So in particular, AI agents make a lot of choices wrong. So whenever they need to make a choice that requires judgment in place, they will make the wrong choice. So we need to intervene. What we also see is that once they have the proper information for the task that they can do, which is maybe 80% to 90%, the spec is cleaner than what we write, actually. So there is a real question mark for that.
Okay, so I think we have a last question by Chao Wei, and then
So thanks, Sean, for the good introduction to Aeneas. You might have mentioned this during your talk, but you said that you don't want to edit the source Rust source code, but that includes also not adding specs or annotations to the source code. I think in the case of cryptography, the specs are given by the RST, so you don't really have to think about including the specs. But in more general purpose, like Rust coding, the user is trying to write his or her own function, and then they may want to write down the specs in that case, and then have a language model derive the Rust code or things like that. Is in this situation, do you think that it's still good to separate the specs from the Rust code, have the specs in Lean, or maybe have a way where the software engineer can actually still see the specs together with the Rust code?
Yeah. No, it's so I don't have a definitive answer today. So what we try, the most important thing we try to do is have a separation between the code and the proofs. And because very quickly on complex code, you have something like 10 lines of code for one line of proof. If the two are interleaved, you can't even read the code anymore. You have a 20 line of code function becomes 200 lines. The engineer can't even read anymore what's going on. So you write it once, you verify it once, but then what happens when you need to maintain it? I think it has a lot of value to put the specs into the code. It also acts as a documentation. Now, how do you do that efficiently? In PR, how do you make it so that you can translate the specs into Lean, and then you can maintain them? I don't have an answer today, but that's definitely being able to write specs in the code is definitely something we're open to. Yeah.
Thanks.
There was one comment.
Yeah,
Yeah.
sorry, it's a comment of the question, so I don't have an answer either, but I have an opinion on that. I think especially for cryptographic primitives, the spec and the implementation are very different. And so the spec is usually dozens of lines, maybe 100 lines for most getting, but and so you don't care and you don't want to have to review the implementation traces. And so they will be low-level annotations on each of the functions. But as long as you get the data vectors on the main function, you don't care about the functions, you don't care about the intermediate, the specs, and so it's quite important, I think, in that case, to have the spec and the theorem at a place where you can just ignore the code. That's not going to get it.
Okay, thank you. So with all this, I think we can thank Sean Ho again